Hello, my name is Ana Beatriz, and I'm going to present some hands-on experience using Python with Geospatial Data Processing and a case study using the IBGE data. Just some background about me. I'm from architecture and made a change to data science. I'm working with data science from 5 years from now, and I work in different industries, and now I'm working in a geospatial analyst a startup with research in FAPESP in São Paulo. Why make this change or to work with mixing and make a hybrid approach using Python and also the no-code tools and no-code softwares, because we have a lot of challenges in geospatial data. We have a lot of data, different source. We have complex data sets and also frequent updates that make this data larger and with frequent different data sets. We have different applications, and these no-code tools have some limitations, and we lack some scalability. So we have a solution. We need, in some cases, do it repeatedly or manually. So a hybrid approach could use Python and open source libraries that Python has a lot. So we can overcome these no-code limitations and enhance the geospatial data processing. And we will see here a case study using the census data from IBGE. So here is some of the various libraries that Python has, because we can use it. Some libraries that was developed to work with this data, but we can also use some libraries from models, because and you can use it into this GIS data. So here we have maps and data viz, a lot of libraries, Folion, Kepler, Matplotlib, and we have data processing, GeoPandas. We have H3 to create this hexagon. We have OpenStreetMap with some libraries that we can use directly into Python, and also some libraries from machine learning and deep learning, for example, and Streamlit, for example, to deploy some applications. So let's go to the coding part. So here we'll see some examples of getting data from IBGE's website, and make some processing and saving, and repeat this process into a lot of different data. So here we are using GeoPandas, Matplotlib, and Folion to visualize this data. So here I already downloaded these files. We can see here in the left side. So we can download it from IBGE, for example, in shapefile, because they have this type of source. Here is a function to retrieve every state, so we can define the state that we want to get from IBGE. And this function just get the file and extract the zip file from shape and get the files into a folder. For example, here, Amazonas state. But using shapefile is not so good to work with these data workflows. So IBGE has the geopackage files. So here's a function to get these geopackage files. And we can give like a list of states that we want to get from IBGE. And here they are downloaded and saved locally. And now we are going to see the state of Pará here. And we just printed the cities that we have here, just to check some things of this data. And we can just get the first rows of these data sets, just to see how was the structure, what is the columns. And of course, we have a geometry column here. And we have all the census data from population, housing, and different things from IBGE. And we can check, for example, the cities of the metropolitan region of Belém. We have like 8 cities here, the number of statistical sectors. We can now work with a data set only of Belém. So we are splitting this data and just using Belém data. so it's more filtered here, but the columns are the same. We can check some statistics and some things that we have in this data set. For example, the number of regions, districts, sub-districts of the city. And we will try to start to work and process this data, format this data. For example, we can change the name of the columns to more meaningful ones, like number of people, number of housing, and just filter the columns that we are going to use in this example here. So we have a more simple data set here. And we can check the data types of this data set. We can see that they are all strings in this case, and of these two ones is like wrongly string columns, so we need to fix that. So we are going to change it to integer here. And we can now make some calculations. So for example, the rate of people per household in each statistical section, and we can create different columns that we want and in aggregate into this data set. So let's check again. We have now these two columns into integer. And then we can start plotting this file. So for example, here we have a simple plot in matplotlib of Belém and all of the statistical sections here. And we have a lot of different libraries to work with plotting. And here just the matplotlib with some settings, for example, edge color, line width, the color of the polygons. And we can use the explore from GeoPandas that is behind it. I think it's Folium. And we can make a interactive map where you can see for each polygon the features of them. And we can work directly with Folium, for example, with some different settings. In this case, when I click in the polygon, the features will be pop-up here. So we have a lot of different types of maps that we can use here in Python. And now we can start to work with these polygons and start to making some functions. For example, in the city of Belém, we have 8 districts here. So we can create a different data set with these districts and make the aggregation of the features. And for example, I'm defining, it's a definition of the sum of the number of people and number of housing. We can use median or different types of aggregation functions. And then I create the rate again here. So now we have another data set with only 8 rows, and each row is the district and all the features of these districts. And we can plot to see the difference here. So here's the original one with the statistical sections. And here is the districts aggregated. And we can plot one above another and put the names of it. So the names of the districts and the statistical section behind. And we can plot using a column value, for example, defining the number of people, number of housing. And we can see what was the most density area, or what was the most area with the most number of buildings, for example. We can plot the new column, the rate of people per household here. So we can see what is the most density district of Belém. We can make some geometric calculations with the geometric column. But first we need to check the CRS of this data set. For example, here from IBGE, it came from a data set with a degree unit. So we need first to convert into a metric unit. Then we can make these calculations. And here we have meter units. And we can create a column in the original data set using the area. Here we have like the biggest one and the smaller ones. We can create a column to define the centroid of each statistical sections. But we need to specify in this data set, in this case, in GeoPandas, to what would be the geometry column that we are working on. So here I created a different data set I use this to allocate the centroid points as a geometry. And then I will convert this centroid back to the degree unit. So here I can plot the centroids of each statistical section, so we can work with this type of data. And one of the things that we can do and can be useful is to allocate some points, for example, some buildings or some points in the map to a specific statistical section of IBGE. So here I created some random points. It's a different data set with 3 random points. And here I will plot them in a zoom plot behind the statistical section of IBGE. So we have these 1, 2, 3 points here. And we want to allocate them to a specific statistical section. And one approach could be we can use the directly statistical polygon from behind. So we will just do a spatial join just to check what is the specific polygon behind this point. So this could be one approach. And here here I have the 3 points and the ID of the statistical sector. And here I will plot the 2 files with the specific statistical sector that each point was. So the 1 was the blue, and 2 green, and 3 the purple one. So, but imagine that we don't want to get the polygon from behind, and we want to check what is the most closest centroid from this point. So what is the polygon that makes the most influence into this point? So maybe you can check if they are closest to the centroid of this statistical sector. And here we are going to make a loop to find the closest centroid to this point. So we will test each point into each centroid, and we will check what would be the closest one. So here we identify each point to the closest one. We create a data set. So we have the original statistical sector, and then the ones with the closest centroid. And here we will plot again. And in this case, the 2 and the 3 points was in the same statistical sector, but the 1 was changed to this red one. So probably it could be more influenced by this polygon and these features of this polygon, and could be a best fit for my case, for example. So this allocation could be very flexible. You can make different functions here, and depending on the case. And we can save these files, of course. We are going to save it. We can save it to GeoPackage again, GeoJSON, GeoParquet, and of course shape files also. So now we have these 2 files here in the output. And the better part is that imagine that we want to make it into all of these cities of the metropolitan region of Belém. We want to make all this formatting and configuration, so we can create a function with all the steps that we made before. So filter the columns, rename the columns, use the numeric format for the statistical columns, and create a different data set with the districts. So we have the aggregation function here. And we want to create a column with the area. We want to create a rate of each one of them, the city with the original polygons, and the file with the districts. And we want to save it here. So first we define this function. And then we're going to process it with the para state. So first it will read the file that we have, and then start doing all the format into each of the cities of the metropolitan region of Belém. So now we are saving these files. So for each city, we have 2 files, one of the city processed and one of the city with the districts processed. Here we can just check one of these files from a different city. And we can make into another state, for example, Acre with another region. We can process all of the files of this specific region of Acre. So now we can see these files in QGIS, for example. So here we have the folder that I saved before. So here is the original one from IBGE. So it came like this directly from IBGE. And now we have a specific one with only Belém. So for example, we have only this file if we want to work with one specific city. And we also have the districts of Belém here. So we have 2 files. And if we want to work with some districts or some of the cities here. So this was one example. So how could be the advantage of integrating Python to geospatial workflows? So we have all this flexibility to define the functions that we want, the approach that we want to make into these files. And we can have some innovation in solutions. We can have new products, new services. We can apply machine learning models with this data. We can work with complex and large data sets because we are not rendering these files. We are working only with the data set. And we can scale the solution, and we can have less human error if we want to automatize some processing. And we can start we can start using steps by step, so we can start downloading and then formatting these files and then working in QGIS, for example. So we can combine this solution using traditional softwares and Python processing. And of course, we can scale the solutions. So. And these are our contacts. I'm working in linkage that we are applying some of these with Python, some of the solutions. And here is the code and the contacts. And thank you.